So this is what's called burying the lead. I mean, this is a good example, right? A better teacher would have worked this first and then showed you the secant cubed and the other thing, right? But, you know, you're stuck with me, so. Ha ha ha. Sorry. Any questions about this one? I mean, there's the obvious question, could you please put this one on the test? There's that. Some of you don't agree with that entirely yet. You haven't embraced the idea that this is an easy example yet. Easy is a loaded word, right? Nothing's easy if you don't understand it. So, yes, sir?
Where did you get the original data on top of
That is the part that requires, that's just, it's thinking. I mean, that's the creative leap. But it's not, I mean, there is, you know, again, integration is a systematic program of educated guessing. Here, my education involves this table. So I look at this table, I go, aha! It's something inside the radical is, after I complete the square, I see that it's of the form sum of squares, right? And I just didn't feel like trying to do the I tell you, we can try to do this with hyperbolic substitution, see how it goes. This would be what? If I was to try to do the same example with a hyperbolic substitution, how would we do it? That might be fun. Tell you what, I won't do exactly this example. I'll do something like it. What if we had, I'm sorry, have I answered your question though? The answer to your question really is, that's why I was going over this table, to try to show you the different patterns we have to work with. So it's somewhat a problem of pattern matching. If I have something that's like a square root of a sum of squares, I could either use a tangent substitution or a sinh substitution. In contrast, over here I had a difference, x squared minus something, that suggested a secant substitution or a hyperbolic cotangent substitution. Let's see here. Let me try to do something similar but different. What if I had something like dx over, say, x squared plus 6x plus, I don't know, 10 to the 3/2. All right. So this is dx over x plus 3 quantity squared. Oh man, it's still pretty easy. Oh, I was trying to make this more cluttered. Let me make that 11. I want to make our life unpleasant for a second here. Square root of 2, no. I don't want to work with, no. I'm not making that square root of 2. No, not that cluttered. This is enough clutter. If I do that, then I have to add 2. Oh, you were saying it's a square root of 2 squared. Thank you. Yes, you're right. Sorry, I was trying to interpret your comment as something more malevolent than that. But in fact, your comment was not in fact not malevolent. It was well intentioned. Yep. And then so let's go hyperbolic. Your way of teaching is so hyperbolic. Why, thank you. Let's see here. X plus 3. I think I would like to choose the square root of 2 times, I don't know. I need to get glasses. Focus. Sinh, yeah. Now if we do that, then what I've got myself, I've got an x plus 3 quantity squared plus 2 is 2 sinh squared phi plus 2, which by the way is 2 hyperbolic cosh squared phi. I do have this general umbrella of thinking. If a problem is super easy in trig substitution, I'm sorry, this is super easy. If that's offensive to you, I'm sorry. You know, these education people, they get really worried about, I'm increasing your math anxiety by using this word easy. You should understand, when I say something like easy or clear, I'm saying it from my perspective. I am well aware that some of you are lost. That's okay. You need to work on homework, ask me questions, blah, blah, blah. And if you think everybody else in here knows what's going on, don't worry. They're trying to intimidate you with their false confidence. No. Listen, if we all knew this stuff, we wouldn't need to take the class, right? So that discomfort you're feeling, it's called learning. It's a good thing. You want that. It's like exercise, right? I mean, I wouldn't know, but I've heard that when you exercise, there's this like discomfort that comes from the muscles breaking down and then growing back stronger. Like you need to do that, but with your brain in here. Es bueno? Yeah, I think that's it. So this is what? Dx is root 2 cos phi d phi. And then down here we've got the 3/2 power of 2 cos squared phi. What do we get then? We've got square root of 2. Let's see, what's 2 to the 3/2 power? Well, I'm just going to write it as 2 to the 3/2 power, if that's okay with you guys for the moment. Let me simplify that a little bit. 2 to the 3/2 power is what? It's 2 root 2, right? And then we got ourselves cos phi d phi divided by what? Divided by cos cubed. Of course, the root 2's cancel, right? I'm going to work this way since I'm running out of board that people can see. This is 1/2 integral of, this guy? Oh, what I was about to say is that, and I got distracted with some sort of nonsense comment about education, sorry about that, is that if it's easy in the trig substitution, it's also easy in the hyperbolic substitution. In some sense, sometimes a lot of times the difficulty level is somewhat reflected. It's not universally the case though, like that secant cubed example, I feel like we kind of do better on the other side of the substitution. I don't know. I don't have anything universal and overarching to tell you about that. What differentiates to hyperbolic secant squared? Yeah, how did that go? dd phi of tanh phi is what? dd phi of sinh over cos, right? Which is cos squared phi minus sinh squared phi over cos squared phi. Okay, apparently it is. I couldn't remember if there was a minus or not. There's some unexpected minus in one of these. I can't remember which one it was. Not this one though. So this is in fact 1/2. It was the secant. Oh, okay. So this is 1/2 tanh phi. Thank you for that. Okay, but then what's the triangle look like here? X plus 3 over root 2 is sinh phi. So that makes the opposite x plus 3, the hypotenuse root 2. And then I gotta, oh, did I erase my, oh man. Well, I'm gonna cheat. It's gonna be the square root of x squared plus 6x plus 11. I didn't really think through it, but if this is right, it should be that what's in the adjacent side minus what's in the opposite side should be equal to the square of those, the difference of the square of this and that. The difference of the square of the adjacent side and the opposite side should again be the hypotenuse squared. And this squared minus that squared is in fact 2. That's good. Now tanh phi then is what? This is 1/2 x plus 3, right? Divided by the square root of x squared plus 6x plus 11 plus a constant. And there you go. Yeah, so they both, so this kind of integral we could go either way. Yeah, wouldn't really make much difference. I do think that trig is a little bit easier here just in terms of what we're familiar with.
Can we just use whatever one we
Yeah,
choose?
of course. I do want you to understand both, but unless I, constrain you otherwise, you're free to use whichever. Now I do have, well, that's not entirely true. In the homework, I have specifically given you 4 problems that I wrote that I want you to use hyperbolic substitutions for. But the ones in the book, you're just expected to use trig because the book doesn't treat the hyperbolic substitution explicitly. But if you look in course content, I posted something, right? Those 4 problems. Yeah, so. Any questions?
Sir, yeah, I'm kind of lost in like how we go from the triangle equation to the equations that triangle kind of come out with.
Well, the point of the triangle is that it captures the relation between different algebraic expressions and the trigonometric expressions. Like once I say tangent theta is x over 2, that automatically, because sine and cosine are related to tangent, it means there's all kinds of other things that have to be true about sine and cosine. Those other things are just encapsulated in this triangle. Like once I write this triangle, you can see that sine theta has to be what? Like x plus 2 divided by that, because that's sine theta is opposite over adjacent, and cosine has to be 1 over that. Now those things could be derived from tangent theta, like algebraically, if you just go brute force algebra on identities, like for example, tangent squared theta plus 1 is, secant squared theta. You could use this to figure out, what 1 over cosine squared is, and then from that you could figure out what cosine squared is, and then from that you could figure out sine squared is 1 minus sine squared. But man, it's just so much simpler to write down that triangle to understand what sine and cosine have to be, as opposed to like trying to run through the algebra of it. So it's like I was trying to say, it's a mnemonic to understand a vast web of conspiracies, algebraic conspiracies between things. Let me just run through here, maybe just a couple examples. Number 20. Number 26. I'll just do these 2. I'm not going to do them. I'm just going to suggest a substitution. You guys tell me what it should be. All right, so what should we do here? I would let x equals to a sine theta. I would make that a substitution to do this one. How about number 26? Let me make a u substitution here. This is the integral of du over the square root of 9 minus u squared. Not quite, though. If u is equal to e, oh, wait a minute. Yeah, u is equal to e to the x. Okay, it is. I'm sorry. I was thinking there was a 2 in the u substitution, but I'm an idiot. Because the 2 is just because e to the 2x is what? E to the x squared, which is u squared, right? So this, after we make a u equals e to the x substitution, is that. And then, oh man, it's again, what is u equal to? What trig substitution am I make here? Yeah, 3 sine theta. I was hoping it would be some variety here, but well, anyway, maybe tomorrow I can list like 10 of them and I'll tell you which substitution goes for each one. That's probably a useful thing if I just make a big list of examples and just say this substitution, this substitution, this substitution. That'll be helpful. I know that that's the most seemingly complicated part of this is how do you make the initial substitution. That's why I wrote the table over there, and I'm trying to get it across to you, but that's the hardest part to really have confidence about. Shut up. See you tomorrow.